Begin, we talked in the first lecture about the history of dynamical systems and the logical structure of the subject. And I tried to give you an overview of what the whole course will be about. And we then got into a little bit of math about one-dimensional systems, which are dynamical systems of the form x dot equals x is just a real number. So last time we looked at this class of systems where x, as I say, is just a real number, and we said that you could try to solve them analytically, but often it will be impossible to do the integrals that will arise. If f is a nonlinear function, you may not be able to do the integral that would come up if you use separation of variables. On the other hand, pictures are really easy to use in this context, and that's going to be the approach we'll take all semester. So the approach was to just draw the graph of this function f. You know, so maybe it's some nasty looking function like that. But we said understanding the dynamical system is pretty easy because all you do is think about an imaginary particle that's moving on the x-axis as a function of time. And then this equation would say its velocity is given by this function f of x. So that would mean that when the particle is here, its velocity would be given by this x dot, which is positive, so it would be moving this way. And actually this particle will always be moving to the right, except when it's over here where x dot is negative, then it would move to the left. And then we pointed out that there are these special places where the function crosses the axis, like here, which we called a fixed point, because if you happen to be there, then you won't move. And that would be, in physical terms, an equilibrium state for the system. So we can see what the long-term behavior of this system is. Everything that starts to the right of this point will go out to infinity, and everything on the left will go out to negative infinity. And we could do that without doing any analysis, just looking at the picture. So that was the approach from the first discussion, and I want to go a little more deeply into that now. Yes?
Is it ever possible to reach a fixed point?
The question was, is it ever possible to reach a fixed point? Well, it depends on the nature of the function f. So for the functions that we're going to consider in this course, which have the property that they're continuous and continuously differentiable, then it will not be possible to reach a fixed point. You could approach it and get closer and closer and, so to speak, get there at infinite time. But if you want to get there in finite time, you can't do it with the functions we're going to consider. It is possible. You can make constructions of functions that have infinite slope, for example, and then you can actually reach a fixed point in finite time. But for the most part, we won't deal with those kind of functions. Was there another question? So then, having mentioned this graphical method and then saying that we're not going to do much about analytical methods, I do want to touch on one analytical method that's quite easy and will be helpful to us. So this is discussed in section 2.4 of the book, and it has to do with the idea of linearizing around a fixed point. So here's how it goes. We're going to examine the dynamics close to a fixed point, which I mentioned last time. We'll tend to use the notation x star for a fixed point, and you know, like in this little example, this is the fixed point. That is, fixed points satisfy f of x star is 0. The velocity is 0 there. And so if we look in the neighborhood of the fixed point, that is not right at the fixed point, but on either side of it, we want to see whether a little deviation will grow, as it does in this case, in which case we would say that the fixed point is unstable, or does it decay, bringing us back closer to the fixed point, in which case we would say it's a stable fixed point. And so to do this, we'll say, let's let our x of t be x star, but then plus a little deviation, that I'll call by the Greek letter eta, where we're going to assume that eta is very small in magnitude. And I'll make it clearer in a minute what I mean by very small, but for now just think of some very tiny perturbation. And then we want to derive an equation now for eta to see does this deviation grow or decay. So to do that, use a differential equation. X dot with this choice becomes x star plus eta all dot, and since x star is a constant, its derivative is 0, but eta is not constant, so we get eta dot. On the other hand, it's supposed to be f of x, and that means it's f of x star plus eta. Now, at this point, everything is exact, but still not so clear what's going on because this f is this complicated nonlinear function. So here's where we invoke the idea of linearizing by saying that let's use Taylor's formula here. That is, I'm just going to assume that this function f is smooth enough that I can write down the Taylor series approximation to it in the neighborhood of x star. And so this would give us then f of x star plus eta f prime at x star plus the next term would be eta squared over 2, 2 factorial, which is 2, f double prime at x star. And then there are higher order terms of order eta cubed and so on. But let's just leave it at that for now. There's another question. Yes?
Are all the functions we work with non-convergent?
The question was, are we always going to assume that our functions f have convergent Taylor series, which would be in the jargon of pure math to say that we're only going to work with analytic functions. For the most part, that's true. We will mostly work with analytic functions. We'll also take the attitude that this is an applied math course, not a pure math course, and we're not going to worry about smoothness. That is, functions are as smooth as we need them to be to do whatever manipulations we do on them. And the feeling is if we're going to get in trouble, we'll recognize that in the course of our work. So I'm not going to be doing rigorous math with careful smoothness assumptions. I do try to refer to the smoothness assumptions I need in the book if you want to look into that kind of thing more deeply. But yes, so I'll just be very cavalier in the style of a physicist or engineer where I just assume everything has a Taylor series when I need to. Is there another question? Okay. So, all right, so let's look at this expression over here on the right. Well, first of all, f of x star, notice, is 0 because we said we're not just linearizing around any old point, we're linearizing around a fixed point. So we already have f of x star is 0, as I mentioned over here. Okay, so that gets rid of that constant term. This term is linear in eta, so this is why we speak of the linearization. It's proportional to eta, and although this looks like some complicated thing, f prime of x star, keep in mind that it's really just a number. I mean, it looks like a function, but it's a function evaluated at a specific point, x star, and all it's really telling us is the slope of f at the fixed point, which in this picture would just be, whatever that slope is, f prime at x star. So I have some number times eta, and then some other number times eta squared. And you've probably seen arguments like this elsewhere, that we said eta is very small, and so at this point we want to neglect the eta squared term, because if eta is small, eta squared is really, really small. We want to neglect eta squared compared to eta. And so that's the idea of linearization, that we want to neglect this quadratic term. This term. Now you have to think about that for a second. Also, I'm going to neglect, for the same reason, but even more so, all these higher order terms in eta. But still, you have to think about it just for 1 second. Are we sure we can neglect this term compared to that term? The answer is yes, we can, as long as this f prime is not 0. If it's 0, then this term is not even there, and then this would be the leading term in the expansion. In that case, we better not neglect it. So, but otherwise we can. So if f prime at x star is not 0, the term, this term in magnitude is much greater than this term. For small eta. And so for that reason, we'll just neglect that eta squared term. And that gives us the linearization. So I'll frequently use this notation. This is big O. That's not a 0. That's the capital O that stands for the order of. And neglecting the terms that are of the order of eta squared yields the linearization of the system at the point x star, which is the system essentially that eta dot is a constant times eta, where this constant r is this number f prime at x star, the slope at that point that we've been talking about. And so you see this is a very easy little linear differential equation that we know much about from previous either calculus or differential equations courses. That is, that just produces exponential growth or decay depending on if r is positive or negative. So you would get exponential growth. Eta grows like whatever the initial eta is times e to the rt. Actually, I might as well say equals, because it's not just approximately. It really is equal for the linearization. So we get growth if we have r greater than 0, and then we have decay if r is less than 0. And notice that that's consistent with our picture above. That is, we have here, in this context, we see a positive slope, and notice that that point is unstable graphically, but it's also unstable analytically, because deviations are growing exponentially fast, at least for small eta. So that's the idea of linearization, very easy in 1 dimension. We'll also be doing it later in the course in 2 dimensions and 3. Here it's quite, I don't know, hardly even worth bothering, but okay. Though you may be wondering, what about if f prime of x star is equal to 0? This caveat I have here. What if it is 0? What would we do then? So in this case, there's no information from linearization. By that I mean that if I find f prime is 0 at a fixed point, that tells me nothing about the stability of the point. It could be stable or unstable, or even a kind of hybrid situation where it's half stable. So just to give you a few examples of what I mean by that, consider these 4 different systems. X dot is x squared, x dot is negative x squared, x dot is x cubed, or x dot is negative x cubed. All of those have fixed points at 0. Right? X star equals 0 is a fixed point for all of them. As you can see by just plugging in 0 on the right-hand side, you get x dot is 0. So it's a fixed point. And also notice that we have f prime at x star, which is f prime at 0, would be 0 in each case. And yet, if we just draw the pictures, we can see easily that they have 4 different stability types. In other words, just knowing a 0, just knowing that the derivative is 0 at the fixed point, anything sort of is possible as far as stability. Let's just see what goes on in detail here. Let's take the top one, x dot equals x squared. So again, rather than solving it analytically, we would just draw a picture. X dot equals x squared. We have x dot here. Here's x. You draw the parabola, x squared. And then you see that over here x dot is positive, so you go this way. But also over here x dot is positive, so you're still going that way. And that means that this fixed point is kind of strange. We haven't talked about it yet, but this is a good time to do it. We would approach it asymptotically from the left, and so our convention would be to fill that in because it's stable to approaching from the left. On the other hand, it's unstable from the right. If you make a perturbation away from the point, that perturbation will grow. So this is a half-stable fixed point. It's stable from one side, but not the other. And likewise, if you look at x dot equals negative x squared, that would have this kind of picture, where now it's, the opposite. It's now stable from the right, but not the left. And if you do x dot as x cubed, well, x cubed has a graph like this. And, well, let's see. So this is now positive over here, negative over here. So we just have an honest-to-God unstable fixed point in that case. And finally, if x dot is negative x cubed, well, then the graph looks like so. And it's a stable fixed point. Now, it's not stable in the same analytical sense as our original stable fixed points, which were exponentially stable. That is, you had exponential decay toward them. Here, the decay would be much slower than exponential. It'll actually turn out to decay to 0 like a power of 1 over t. You could check the details if you're curious about that. But so you have algebraic relaxation, which is very slow and pokey compared to exponential. But anyway, it is still stable from the graphical sense. So is there any question about what's been shown or what the point was of this so far? I guess I would say the bottom line is if you want to figure out stability information at a point where f prime is 0, just draw the graph. And that'll tell you what's going on. Or you could, if you really insist, you could do the Taylor series out to a higher order, to x squared or x cubed, or I guess in my notation, eta squared or eta cubed. But I really do think that's the wrong way to think. I think you should look at it as pictures. Okay, let me do one little example of this and then move on. We talked about the logistic equation for population growth, which you'll remember is x dot is rx 1 minus x over k, where x is the population of organisms, r is their growth rate, and k is the carrying capacity. organisms the little system can support. The sort of, I hesitate to call it an ecosystem, it's just this one population. But anyway, so looking at this with linearization, we can see that x dot equals 0 when either x star is 0 or x star is k. Those are our two fixed points. And then if we wanted to figure out their stability, we could look at f prime at x, which I have to take d dx of this, so I'll get r. And then minus, this is rx squared over k. Differentiating that gives me 2rx over k. And then if we calculate f prime at one of the fixed points, at 0, it's just r, which is positive. We're assuming r is positive. It's a positive growth rate. And so this tells us that x star equals 0 is unstable. Whereas the other fixed point, if we look at k, then we get r minus 2rk over k. And the k's cancel out, and this is negative r. So this is less than 0. And so x star equals k is stable. Right, remember the criterion. Negative f prime gives us stability. Positive gives us, oh, I guess my notation's a little nasty there, isn't it? Because I'm calling that r, but that's a different r from this r. But okay, ignore that. We're looking at f prime at x star. So anyway, these conclusions are consistent with what we said graphically, where the logistic equation has this kind of picture of x dot versus x, where we saw that this point at k really is stable and the origin really is unstable. Okay, so linearization gives us the same information. Any question about that? I think then I'm going to leave linearization and talk about a few more things in this second chapter, and then get into the third chapter, which is where things start to get interesting. Okay, so the question came up earlier about can you reach a fixed point in finite time, or can you ever reach it at all? And so this ties in with this pure math notion of the existence and uniqueness theorem for ordinary differential equations. So let me just comment on it. I said something briefly a few minutes ago. You could read about it in section 2.5. And I don't really want to dwell on it, just to say one thing, which is that there's a theorem that you would prove in a rigorous differential equations course that says that the solutions to x dot equals f of x do exist, and they are unique if, I mean, these are not the best possible conditions I'm going to give. There are milder conditions that would also ensure these existence and uniqueness. But for us, it's good enough to say if we have f continuous and if we have f prime of x continuous. So that's when we would say that f is continuously differentiable, if it has these two properties. And so under these assumptions, you can prove then that the solutions to the differential equation exist. Now, that doesn't mean they exist for all time. They might exist only for a very short time after you start them from some initial condition. So there's no guarantee about existence for all time. But the solutions do exist in some possibly small time interval around time equals 0. And there's only one solution. So that's sort of what we want. I mean, that's what we've been assuming in the way we draw the pictures. But if you relax these conditions too much, then you can get some pretty weird pathologies, which I mentioned some examples in the book, but they're not going to really concern us. So, okay, so that's one thing. And then the other that I want to mention, this is a little more interesting, I would say, is this remark. Which is touched on in section 2.6 of the book, which is that if you ask what can these one-dimensional systems do, what kind of behavior can they have, they're very limited in what they can do. That is, if we ask what's the possible behavior of x of t as t goes to infinity for these 1D systems, x dot equals f of x, then the only things that can happen are either, as we saw in the earliest example, where I had that one unstable point and trajectories either went out to plus or minus infinity. You can have that. So either x of t goes out to infinity in one or the other direction, or x of t approaches a fixed point. That's it. And in particular, what's not possible is anything like an oscillation, a periodic solution, even a damped oscillation is not possible. So it's impossible to have something whose time series would look like this, or even a more periodic, like a truly periodic one. Those are not, you can't see that in this class of systems. And you certainly can't have chaos. So these have really kind of boring long-term behavior. They just approach an equilibrium point or go out to infinity. You might say, how do I know that? What about if I think up a really clever f? Are we sure that it's not possible to do something like this? Yes, we're sure. It's true for very easy topological reasons. So let's see why. The reason is that all the trajectories or solutions, whatever you want to call them, increase or decrease monotonically. Or stay fixed. And I don't really know quite how to give you a proof of this in the spirit of the course, where I'm not really proving things, but the intuition is just draw whatever smooth f you can think of. As we said, under a positive hump like this, you just move monotonically to the right till you hit a fixed point. Here you would move monotonically to the left. What's the problem? I mean, why can't you oscillate? Maybe think of it that way. What would it mean if you did have an oscillation? It would mean that pick some value of x that you're interested in. Remember, this is the x-axis. This is x dot. Suppose I thought there was an oscillation where I go through this x value once, going that way, and then when I oscillate, I come back and go this way, to the left. That would mean that the vector field is not well defined here, because it would at some times be pointing to the right when I'm going that way, and it would also be pointing to the left when I'm coming back, and that violates the single valuedness of f. Right? I mean, if f is a function, it only points one way at each point. So you can't go two ways through the same point. That's all there is to it. So there are no oscillations in one dimension. Now you might ask, wait a second, this sounds ridiculous. Of course, I've heard of the simple harmonic oscillator. It moves on the x-axis. It oscillates. So what's the point? Yeah, the point is that the simple harmonic oscillator is not a first-order system. It has x double dot. Right? So the x double dot means that to write it down geometrically, we're going to need two dimensions, one for x and one for x dot, and that'll be studied later in the course. Those are second-order systems. So if you want to think purely mechanically or physically, these first-order systems you should think of as just a force being balanced by damping, by a dash pot. There's no inertia. There's no x double dot term. So if you have some kind of weird nonlinear spring pulling on a mass that is so tiny it has no inertia, and it's just moving through goop of tremendous viscosity, so it's very overdamped, that thing is not going to oscillate. That's just some complicated shock absorber that's just going to go back to its equilibrium. So I don't know if that's clear or not. Do you want to ask anything before we move off of that topic? Okay, so there's no chance of overshoot for these systems, no oscillations. All right, so let's leave chapter 2 and move on to chapter 3. Actually, let's stay here. Okay, now chapter 3 is pretty substantial. That brings up the very interesting and important topic of bifurcations in the simplest possible setting, still talking about these one-dimensional systems. Later in the course, we'll talk about bifurcations in two-dimensional and higher dimensional systems. But for now, let's just focus on these flows on a line. So, all right, what is a bifurcation? Well, think about some system that has a parameter in it, some kind of knob you can turn. Then, like for instance, I imagine this picture. Here's a little support, and then I put some kind of heavy block on it. And I ask, can that block just stay in this vertical position? Maybe if the support is strong enough. But now suppose I make a really big block. I'm putting some gigantic boulder on there. It seems unlikely that this thing is going to be able to hold the heavy weight, and it's going to, tend to, well, this straight structure will buckle. Right? It'll bend to either side. It'll either buckle like this, and the whole thing will come crashing down, or it might buckle like that. But so the straight solution will not be stable anymore, and we'll have something else going on. So this is typical of a bifurcation, that you've changed some parameter, in this case the stress or the load, and you get a dramatic and sudden change in the response of the system as you change this parameter. So as a parameter changes, for us, speaking about vector fields on the line as models of differential equations, as a parameter changes, the qualitative structure of the vector field may change dramatically. For example, a fixed point might be created or destroyed. Or they might change their stability. So by qualitative change, I don't just mean like you move a fixed point around. I mean something much more dramatic than that, that it actually just vanishes and now it doesn't exist anymore, or it changes from stable to unstable or something like that. And so a change of that type is what we would call a bifurcation. And then we also have the further language of a bifurcation point or value. That's the value of the parameter at which the change occurs. So as I tried to hint with that example with the block on the little straight, drinking straw or whatever that thing was, these are relevant to science. So you probably, depending on what field you study, you've run into bifurcations a lot. Maybe not by name. In fluid dynamics, if you have a flow that's laminar and you start turning up the Reynolds number, that flow might start to become wavy in a bifurcation, or then if you keep going high enough, it may become turbulent. Those are important and still somewhat mysterious bifurcations. If you're studying, say, heart rhythms, like people in our vet school work on, there's the normal heart rhythm, which hopefully you're experiencing as we speak. And then if you have a bifurcation to arrhythmia, that would be bad, especially if it's the deadliest kind of arrhythmia called ventricular fibrillation, in which case we only have a few seconds to save you. So the study of bifurcations is pretty important in all parts of science. And so I want to begin our discussion of them with just a few little easy mathematical examples without any scientific content, just to get warmed up. And then in later lectures we'll talk about some pretty interesting scientific examples, one from mechanics and one from population biology. And we'll have many more throughout the course. So roughly speaking then, these are models of instabilities or sudden transitions. So models of instabilities, transitions, and so on. Okay, but first, let's just get warmed up, as I say, with a few of the basics. So the most basic one is a bifurcation that creates fixed points out of nothingness. And it does it in pairs. It's almost like in physics when they talk about a particle and an antiparticle coming out of the vacuum. This is something like what we have, except for us it'll be a stable and an unstable point coming out of the vacuum. So it's for reasons that are not clear at this stage in the course, but will be clear, I hope, later in the course. This is called the saddle node bifurcation. The language doesn't make sense yet because saddle points only exist in 2 and higher dimensions, so we don't have room for them. But this is the analog of what we're going to see in higher dimensions, and we still call it saddle node. So it's the basic mechanism for the creation or destruction of fixed points. And so here's a standard example. That is, this is probably about the easiest system that has the phenomenon in it. Let's look at x dot equals r plus x squared, where this r is what I'm thinking of as my control parameter. That is, if I'm an experimenter, r is the knob that I can turn by changing something in my apparatus or whatever. So I have control on r, and now I want to watch how my system behaves. And so when r is negative, then if I look at my x dot versus x picture, notice, of course, this is the graph of the right-hand side is a parabola, but it has an intercept of r on the vertical axis. So when r is negative, it would look like that. And it's a parabola opening upward. And now you can see that, you know, from our techniques that we've got negative x dot here, positive here, and positive over there, telling us that this is a stable fixed point and this one is unstable. So right now we have 2 fixed points of opposite type. Now imagine that we start turning the knob and r is being brought closer to 0. So imagine that r is only slightly less than 0. Then you'd have a picture like this with the parabola just barely going underneath. So it's still negative, but close to 0. And notice what has happened. Our fixed points have gotten much closer together. So if you were watching a movie of this, you would think of lifting up the parabola gradually, and these 2 fixed points, these intersections, would be moving towards each other ominously. Right? And then at r equals 0, ba-boom, they're going to hit. And so they would collide. And then you would have this picture that we discussed earlier, where it's now just x dot equals x squared with that funny half-stable fixed point. You can now kind of understand, by the way, where that funny half-stable fixed point came from. We were catching a system at the moment of bifurcation. And the stable and the unstable ones have merged, and that's why you've got this half and half character here. And then finally, when r is greater than 0, well, now the parabola is above the axis and the flow is everywhere to the right. It's just there are no fixed points. They're gone. So it's as if after the collision of the stable and unstable point, they have now annihilated each other and they're gone. And so we went from 2 fixed points to 1 of this weird hybrid type, and then 0. All by continuously changing r. Okay, so I hope you would agree that's a qualitative change. Here's a system with no fixed points, and here's one where you can get stuck in 2 places. Yes? Do stable fixed points arise? Oh, half-stable. I'm sorry. Do half-stable points arise only as a result of bifurcations? I think that would be fair to say. Yeah, they don't. You wouldn't normally. I mean, if you have implicitly, there would be some parameter in the problem which, if you changed it, it would take that half-stable fixed point and make it either into nothing or into something like that. Or it depends on how the parameter is introduced. We'll see other mechanisms for creating half-stable points besides this one. But I think it's safe to say, yes, it's always a result of some bifurcation. Is there another question? OK, so that was the saddle node bifurcation. And there's a standard way of representing it. that is, you could show the sequence of pictures, but there's a little diagram that everyone draws called the bifurcation diagram that encodes all of this in one picture. So a bifurcation diagram would be something like plot the curves of x star versus the control parameter r, where we think of r as the independent variable. That's the thing under our control. And then we watch what x star is doing. So in this case, by just setting x dot equal to 0 to find the fixed points, we see r plus the fixed point x star squared is 0. And so the graph of that, let me just call this x, not quite x star, because the x star is going to appear as the curve. X star would be plus or minus, the square root of negative r. And so over here it would look like this. Now I'm going to just draw a dotted line for now, because I want to concentrate. One of those is going to represent a stable fixed point, and one represents an unstable fixed point. But let's concentrate for a second to see which one is which. How do I tell? Which one of these is stable? Is this branch stable fixed points, or is this? Do you see how to think about it? You want to put up your hand? Yes, you have. Looks like you have an idea. Yes, the comment is the stable fixed point is the negative one. So in fact, in this picture, this must be the stable branch. Right? It's always the negative one that was stable. So our notation is that we use a solid line, sort of in the same spirit as a solid dot, for the stable branch, and then we would use a dashed line for the unstable one. So to make it a little more visible, let's just make some big dashes here. And it's also sometimes helpful, although not really necessary, to draw some arrows. That is, we know that we're, think of holding r constant, then that would mean that you're just on some vertical line in this picture that represents the x-axis at that choice of r. And so you would say, like in this slice, you'd be going this way, and like that. So you can add that if you want. Now it's a little distracting. The x-axis is the r-axis is a meaningless artifact in this picture, which probably shouldn't really even be there. But okay, so there it is. And then what else? And then over here we're just going this way, up, up, up. Okay, so anyway, that's the bifurcation diagram for the saddle node. And people use other words for it. Sometimes it's called a turning point bifurcation, because in this picture it looks like this branch is turning around and then becoming unstable. Or it's also sometimes called the fold bifurcation, because it looks like you took a straight line and folded it to make this parabola. So you'll hear words fold or turning point, but I'm going to call it the saddle node. Any question about this? Yes? The dashed line here refers to these unstable points. So this unstable point, if we calculate it, this is at x star is the positive square root of negative r. And so that's why it's up here at the positive square root of negative r. This doesn't mean flow on the picture. I'm just indicating it. Maybe I should make it look like this. Whoop. There. Any other comment or question? Okay, so that's, as I say, the standard example, like the most pristine example of a saddle node bifurcation. Now, in real life, or in typical practice, you would not see it so cleanly. So let me show you a type of question where it's more like what you might encounter in your own work. Let's look at this example. Suppose I gave you this differential equation. X dot is r plus x minus natural log of 1 plus x. Okay, so there's some fairly nasty right-hand side nonlinear term, log of 1 plus x. We want to analyze that as a function of r. What's going on with that system as a function of r. So you could, your first thought is, well, let me figure out what the fixed points are, since they dominate the behavior of these one-dimensional systems. And so the fixed points would satisfy well, the right-hand side has to be 0. So we have r plus x equals log of 1 plus x. Or those, I guess, we would put as x stars. And already, you kind of feel like, well, it's not so easy to solve for x as a function of r. In fact, I tried to make it so that it's impossible. That is, you can't invert that, I don't think, algebraically for x of r. So if you're stuck in this old analytical way of thinking, you feel paralyzed at this point and you just give up. But of course, we're graphical, not analytical in this course. And so we would say that's actually pretty easy to understand because I can draw the graph of both of those and then figure out what's happening. That is, let me, even though I can't solve for x star of r, but a simpler approach is to just use a graphical method where what we're going to do is plot both of these functions. Let's plot y equals r plus x and plot y equals log of 1 plus x. And so you'll remember on the first day I said that you have to be good at curve sketching in this course. It's because of things like this. If you had to use your graphical calculator to draw y equals log of 1 plus x, you'll just be slow and you'll be at a disadvantage. So try to have the basic functions and their shapes in your head, or at least be good at figuring out what they look like. All right, anyway, maybe you do know how to draw them both. And so log of 1 plus x is going to just look like the log function except shifted over. So it's sort of like this. And I'm thinking of this as y now. This is not x dot. Okay? That vertical axis just represents some made-up axis y that I'm using to graph these two functions. And the reason for doing that is, well, log of 1 plus x is there. R plus x is a function with its graph has got a slope of 1 and an intercept of r. Right, just a straight line with a slope of 1 like that. And you see that these two curves don't intersect at the moment. So what does that tell us? Well, if they don't intersect, it means that this is not equal to that for any x. So we don't have any fixed points when r is like the r in the picture. On the other hand, you could imagine as you start changing r, which would mean sliding the line down but keeping its slope at 1, you can see that this line is going to bang into the curve at some point. And we could draw a sequence of different pictures. Here it's almost hitting. Here it's tangent. Here it has hit and now has two intersections. So do you see that that's really the same scenario as what we talked about? That there's no roots, then there's one root, and then there's two. Went from 0 to 1 to 2 fixed points. That's what happens in the saddle node bifurcation. So in fact, you can now see that this system does have a saddle node bifurcation. saddle node bifurcation occurs when, what would be the condition in geometric language? When what happens? Is it obvious? You don't want to say? Go ahead, you could say in the back. Yeah, well, if the line intersects the curve tangentially, right? So if there's a tangential intersection, now we have to think about when does that happen, and so it's when two things happen. On the one hand, we have that condition, which says that an intersection occurs, and it should be a tangent intersection, meaning that the line and the curve have the same slope at the points where they meet, at the single point where they meet. So it's not just that this is true, but also d dx of r plus x should equal d dx of log of 1 plus x. You need both. The tangency condition is the second one. Right? They intersect with the same slope. And so now we can calculate where does that occur in the sense of where in the parameter r and where in x. So we already know that we can't really solve this first equation. The second one is going to be easy. So let's take those derivatives, and we get 1 equals derivative of log of 1 plus x is 1 over 1 plus x. And so that has a solution x equals 0 at the bifurcation. And then the corresponding value of r is given by r plus x equals log of 1 plus x, when x is 0. So this says r is equal to log of 1, which is itself 0. So let me call it r sub c for r critical, like happening, that's the critical value of r. Critical or bifurcation value. And notice my picture was actually pretty good. That is, it looks like it's occurring at r equals 0, x equals 0, that we have a tangent intersection, and I tried to draw it reasonably correctly. One last thing about that. Now that we know that the bifurcation occurs at 0, 0 in this picture, let me show you what happens if we expand the vector field around 0, 0. So that is, notice that so near the bifurcation, at xr equals 0, 0, x dot, let me do a little Taylor expansion on the x dot itself and keep only the leading terms in r and x. So actually, maybe it's clearer to write it this way. Let's just reproduce what x dot is. It's r plus x minus log of 1 plus x. But then keeping the leading behavior in both r and x, the r we don't want to get rid of, even though it's small. We got to keep something that tells us about r. But then hopefully you remember that log of 1 plus x has a Maclaurin expansion, which is what? It's x minus x squared over 2 plus x cubed over 3. Like that, I think. Is that right? Yes, that's right. Valid for x less than 1 in absolute value. Okay, and so if we just think about very small x, then this is behaving like r plus x minus, and then using this expansion, x minus x squared over 2 plus x cubed over 3, etc., which simplifies to, notice the x's cancel out, and I get r plus x squared over 2. And then there are other terms which are of order x cubed and higher, but those are negligible compared to the x squared term. What I'm trying to show you here is that near the bifurcation, we get a vector field that looks familiar, right? R plus x squared. Forget about the 2. This looks like when we did the standard example for the saddle node, we had r plus x squared. We're getting that same thing again near the bifurcation. And so people refer to this r plus x squared example as a normal form. And there's a whole theory about, you know, what the vector field will look like near a saddle node bifurcation. That gets technical, and I don't want to really give you a precise statement of it. But in the crudest sense, the statement is something like that near a saddle node, the dynamics always looks kind of like a constant times r plus a constant times x squared, you know, plus or minus a constant times x squared. That's the generic behavior near a saddle node. And that's one reason why we're studying these simplified standard examples, because they're very typical. Want to ask anything about that before we? I want to show you one or two other bifurcations before we quit. Okay. Yes? The bifurcation diagram will pretty much always look like a sideways parabola. It won't be exactly a parabola, only right near the bifurcation. Like if you drew the bifurcation diagram for this, it would reflect that logarithm, so it wouldn't give you a perfect parabola. But yes, it will have a bend, and it will look qualitatively like that. It might be bending this way, or it might be bending that way. You have to check the details. Is there another question? Okay, so let's talk about two other bifurcations that come up frequently. There's quite a bit of jargon here in this part of the subject. That is, these bifurcations have not so memorable names, and we're stuck with that. Different sciences were developing bifurcation theory at the same time. People in fluid dynamics had their own words. People in math have their own words. So, but the words that I'm going to use are now more or less standard, I would say. Okay, so the second bifurcation to discuss is commonly called a transcritical bifurcation. And its normal form is slightly different from what we just talked about. So earlier we had x dot was r plus x squared. Now it's going to be rx plus x squared. Actually, let's make it minus x squared. This doesn't really matter. This is just the algebra looks a little easier this way. Notice the big difference that now instead of r being by itself, it's r times x. And it makes a big qualitative difference in what's happening in that this now factors as x times r minus x. So you see that there are two fixed points. X star equals 0 is a fixed point for all r. And the other one is x star equals r. And so this bifurcation comes up, where, as I said, the first one, the saddle node, was the mechanism for creating and destroying pairs of fixed points. this is what tends to come up if you have an indestructible fixed point. Like here, x equals 0, you can't get rid of it by changing r. It's always there. Okay, and there are some situations where there will always be some fixed point for all values of the parameter. So it's a fixed point for all r. Let me use that symbol for all. We use that to save a little bit of writing. And cannot be destroyed. You could think of scientific examples where this would be natural. Like if you're doing a population biology problem, it's very common that if there are no organisms of a certain type, then there will never be any organisms of that type. They don't just spontaneously get created out of the atmosphere. So 0 tends to be a fixed point in such a problem. That doesn't have to be a biological population. You can be studying a population of atoms in a laser, and then that might also have this character. Actually, there's an example in the book in section 3.3 of a laser model where the bifurcation that creates the onset of lasing is a transcritical bifurcation. So take a look at that if you are interested in optics. But here, let's just look at what happens in this problem. Even though we can't destroy the fixed point, we can change its stability. And that's what happens here. So let's draw the bifurcation diagram. Maybe as a little use of linearization that we talked about earlier. Let's see what's going on. I mean, x equals 0 we can see is stable. That is, this system has a linearization. If we look at f prime of x, it would be d dx of rx minus x squared. That's r minus 2x. And so f prime at 0 is r, which says that x star equals 0 is stable when r is less than 0 and unstable when r is greater than 0. And so let's draw a picture. Let's just go straight to the bifurcation diagram. Here's r, here's x. And we can see the fixed points pretty easily. We know that they're 0. So let's just put in something here along x equals 0, and then x equals r is the other. So that's this diagonal line. So we have these two sets of fixed points meeting in this cross-shaped pattern. But we just said that x equals 0 is stable when r is negative. So I'll draw this kind of heavy. So those are stable fixed points there. And then we could also check the other fixed point for stability. F prime at r is going to be r minus 2r, which is negative r. It's interesting. Its f prime is the opposite of this f prime. So when this one is stable, this one is unstable, and vice versa. And that means that in this picture, this would be heavy. And so now you have this funny bifurcation diagram where there's this unstable branch along here. This is supposed to be on the r-axis. And then this is also unstable here. And the flow is like this. So people frequently use the term exchange of stabilities if they don't say transcritical bifurcation. In some of the older literature, you'll see this name. Or I guess what you're kind of thinking of is that this is one family of fixed points and they were stable, but then when they collide with these guys, they exchange stabilities. Now this stable one becomes unstable and this becomes stable. So it also sort of looks like particle physics, doesn't it? Two things banging into each other. But okay. Yes, you have a question?
At R0, you have a
Good. So what's going on at r equals 0? So I've drawn it pretty decisively heavy there, but I shouldn't, should I? I mean, what is going on at 0? Well, I don't want to put a circle there. It's not a fixed point per se. But what is happening? Well, just look. At r equals 0, it's x dot equals x squared, negative x squared. So yes, back to your earlier question. This is giving us another half-stable fixed point. And it's, again, because a stable and an unstable point have collided. But notice that what's different now is since when they collide, they merge right at r equals 0 and give us this half-stable point. But then they don't annihilate. They sort of pass through each other, except they change flavor. So that's another kind of bifurcation. Okay, let me show you the last one I wanted to mention. And then we'll pick up on scientific examples of this next time. So the last one is the pitchfork bifurcation, which tends to occur in systems with symmetry. Very frequently, the symmetry will be left-right symmetry. Like in that buckling example, the weight could buckle to the left. The support could buckle to the left or the right. So let's look at, say, something like this. X dot equals Rx minus x cubed. This has a symmetry where whatever is happening on the x, it has symmetry between x and minus x. Mirror symmetry in that sense. Let's just look at the vector fields to see what's going on. So if I draw x dot versus x, here's an interesting case. Let's look at the case where the r is negative. All right, I mean, this picture is, I'm trying to draw Rx minus x cubed, where I've screwed up, haven't I? Yes, because this should not look like x cubed. I want negative x cubed. So let's start over with that. Yeah, let's try that again. So when r, how about I just build my way over to it. If r is negative, I have something that goes through the origin with a negative slope and then otherwise looks like negative x cubed. So it sort of looks like that. Not drawn so well, but okay. So we just have a nice garden variety stable fixed point at 0. Then when r is 0, I would have negative x cubed, we discussed earlier, has a stable fixed point, but of this algebraically attracting kind. That is, it's not really aggressively stable, not exponentially stable, but it's still stable. But then the interesting thing is when r is positive, then our picture comes through here with a positive slope and then looks cubic out there at large x. And what's amusing is that now we have this symmetrical pair of fixed points. That is, here at x, so you can see by factoring it, right? I mean, it's x times r minus x squared. So here at x equals square root of r is one fixed point, and then it has a symmetrical partner. X is minus square root of r there. And these are both stable. Whereas the origin has now become unstable. So what's interesting about this is that, remember with the saddle node, we had 0 going to 1 going to 2. Then with transcritical, we had 2 going to 1 going to 2. And now we have 1 going to 1 going to 3. It's interesting. And they occur in this symmetrical pair because of the left-right symmetry. So this kind of thing is, in the jargon, called a supercritical pitchfork. Supercritical is a word that you see a lot in dynamical systems. It means that the bifurcating solutions are stable. So here the bifurcating solutions refer to these two new fixed points that have bifurcated off of the original fixed point at the origin. And the reason for the name pitchfork is that the bifurcation diagram looks like this, where this is stable. This as a function of r. Here's x. This is stable. Then these guys are stable. And this is unstable. So you're supposed to think, if you're not really a farmer, that this looks kind of like a pitchfork. Although don't pitchforks usually have more tines than just 3? So yeah, all right. But we're city people, I guess. Okay, so that's it for now. Next time we'll talk about some scientific examples of bifurcations. Okay, thanks.